So now that we have derived the expressions for the quantum Hamiltonian and the quantum momentum operator, we can go back and see if our guess or our assumptions about how a scalar field transforms is true when we quantize the scalar fields. So remember that classically, if I make say, a Lorentz transformation where x goes to x prime, where x prime is the Lorentz transformation matrix acting on x, or if I do a translation of x where x goes to x prime, x goes to x plus a mu, then at least we have shown it for this case, the scalar field phi of x changes to a new scalar field phi prime, whose value at x is given by the old scalar field phi with the argument given by x minus a. A similar logic tells us that under the Lorentz transformation, phi of x should go over to phi prime of x, but the argument of the right-hand side will be phi, the inverse transformation acting on x. Now let's see how these things, what becomes of these transformations for the quantum case. So for the quantum case, we're just going to look at the transformation where we're just going to do the transformation for the translation. So for the quantum case, we take x2, go to x prime of mu, which is x mu plus a mu. Now, according to quantum mechanics, we expect the operators to transform in this way. If phi is an operator, then it'll transform to, it'll go to phi prime, and phi prime will be given by some unitary operator, which is a function of the parameters a, acting by conjugation on our original field phi. So this is what we expect from general quantum mechanical consideration. I mean, this comes from the fact that, for example, what is u of a? U of a will have the form of exponential of minus I times the parameter a mu times the conserved charge p mu. So this is what quantum mechanics tells us. So for example, if we have an operator at time 0, if you want the operator at time t, then that's given by phi of t should be given by the time evolution operator acting on phi, but by conjugation. So this would be u of t, and this would be u of t dagger. And you can check that this sign is the correct sign for the time evolution operator, because as you know that the time evolution operator is given by u of t is equal to exponential of minus I times the Hamiltonian. So this is the equation that we want to investigate in detail, and it suffices to look at the consequence of this equation for infinitesimal a, because we can always build up a finite transformation by making many, many, many infinitesimal transformations. Okay, so let us remind ourselves what the p operator is. So p is now the quantum operator. So the p operator, we are just going to, it's quantum. We are going to just drop the quantum label because everything here will be quantum unless we specify otherwise. And this is given by the usual, Lorentz invariant measure And it has to be Lorentz invariant because it will be part of a 4 vector. So and here we have k mu, a dagger of k, a of k. And incidentally, this also shows us why the Hamiltonian, which is the zeroth component of this thing, so the Hamiltonian is H0, the Hamiltonian is P0, why the Hamiltonian was not a Lorentz invariant quantity. Well, that's because the Hamiltonian is the zeroth component of a 4-dimensional vector operator. A 4-dimensional vector operator, this is the zeroth component, and the other 3 components are given by pi. And of course, under Lorentz transformation, this should transform as a contravariant vector. And that's why the Hamiltonian should not be a scalar quantity. Whereas on the other hand, if I look at the Lagrangian, and I can even look at the quantum version of the Lagrangian, that is a scalar. It is not part of a 4-dimensional vector quantity. Anyway, so let's come back to this thing and see how this acts on some field phi. So we are interested in U dagger of A phi, and then we have U. This is phi of x, and then we have U of A. Now, for small values of A, for infinitesimal values of A, what we can do is that we can expand U of A. So U of A will be, well, there'll be the identity operator, and then there will be A, I times A mu times P mu. A mu, P mu, where P mu, the mu is downstairs. So now if I look at what U dagger is, so U dagger of A will be given by 1 plus I, A mu, P mu. So that, U dagger times U will be the identity operator plus correction terms, which are of the order of A squared. So now this equation, if I expand it up to linear order in A, then this becomes U dagger A phi of x U of A gives me the first term is just phi of x, and the second term is going to give me I times A mu times the commutator of P mu and phi. So we now have to evaluate this thing. So what is the commutator of P mu and phi? Well, let's just write them out. So we can do we can expand them in Fourier space, and then from the P operator we are going to get K mu, the eigenvalue, and then we're going to get K mu, and then we're going to get A dagger of K, A of K, and from the phi operator we're going to get 2 terms. The first term is going to be A of K prime, and that's going to give me an exponential factor of minus I, K prime x, and the second term we are going to get again K mu, A dagger of K times A of K, and commutator with A dagger of K prime, and then we have an exponential of plus I, K prime x. And then we can factor out a few things. We can factor out K mu from both terms. And then what we can do is that we can write this thing as A dagger of k commutator with A of k prime times A of k times e to the power minus I k prime x. How do we do this? So we are just writing this term. What did we do there? What we did there is to note the fact that if you have a commutator of A times B and C, we can expand this and we can write this as A times commutator of B comma C plus the commutator of A and C times B. For the second term, we can write that there'll be a commutator. Well, first there'll be an A dagger of K, and that'll be just this term, and then there will be a commutator of A of K, and there'll be a commutator of A dagger of K prime, and there'll be e to the power I K prime x. Sorry, I just realized I misspoke. When we were working out this term, it's this thing which will have commutator of two a's, and so this is this first term which will be vanishing. The second term, this guy, is what is going to give you this. Okay, so from each of these terms, I get only one commutator, and these can be evaluated easily. So here we have the integral of dk and dk prime, k mu downstairs, and here we see we have a dagger a, so there will be a minus sign coming from here. We'll get a minus sign, and we'll get a 2 pi cubed and 2 of ek, and then we'll get a delta of k minus k prime, and then I get a of k e to the power minus I k prime x, and then from the second term we get a dagger of k, and then we get 2 pi cubed, and then 2 of ek delta cubed, del cubed of k minus k prime, and then I get e to the power I k prime x. So now we can use the Dirac delta function here and here to do one of these integrals. Let's do the dk prime integral. And if you do this, of course, this guy will cancel out with one of the 2 pi cube. This will also cancel out. So when the dust settles, what we get is d of k tilde times k of mu. This is this guy. And then the first term, we get minus of a of k e to the power minus I k of x. Now k prime becomes k. And then plus a dagger of k e to the power plus I kx. This is what we get. And so then what we can do is that we can just like write this as d of k tilde, and this thing we can just write this thing times the signs. We can just write it as minus I, the derivative with respect to x mu. And inside we have a of k e to the power minus I kx plus a dagger of k e to the power plus I kx. And you can see that if this thing acts on this guy, it brings down a factor of minus I k, and minus I gives me a minus sign. And if this thing acts on this, it gives me a factor of plus I k, and that multiplying with this minus I gives me a plus sign, which is this sign. So we have written this guy as a derivative and changed the signs here and here accordingly. But now, this is an integral over k, so I can just factor out this derivative operator. Then I have minus d by dx mu acting on phi of x. And therefore, what I've shown is that, phi prime is equal to phi, and then we had a plus of I there, and then we had an a mu, and then from the commutator we get minus I del of del x mu phi of x. And so we can write del of phi, which is phi prime minus phi, is equal to plus a mu del mu of phi. So we see that although we made the transformation where we took x to x plus a, phi went to the operator phi went to phi prime, phi of x went to phi prime of x, and this was given by phi times x plus a. This is exactly opposite what we expected from the classical field theory result. So what is happening here? So what's happening here is that when we are doing a classical transformation, what we were doing is that we took some fields which already had some values, because classical fields have some well-defined values, and when we made the transformation, it changed the value of that field. But whereas here, when we make this transformation, we are not changing a classical field, we're changing quantum operators, which will then act on some Hilbert space. So what we're changing is how the action of that operator on the Hilbert space of particle states. So this is a very different has a very different physical interpretation. And therefore, it is not surprising that this changes in a different way. However, it changes in a way, the quantum transformation changes in a way which is completely consistent as well. And as we go to more interesting, more complicated operators such as spinor operators and vector operators and tensor operators, we will see kind of the nuances developing in this story.